All right, so let's get to mathematics. So I want to talk about Leavitt path algebra, and I don't know how many of you in the audience know about Leavitt path algebra. So I'll assume that you don't know, and I'll explain everything. So there are two motivations here. First is a very basic fact from linear algebra that we know. Something that you learn early on in linear algebra is that if you have a finite dimensional vector space over a field, then any two bases have the same number of elements, right? So if K is a field, then you have these two isomorphic implies M equals N, right? But the situation is quite different in the case of an arbitrary ring. If you take a free module, so suppose R is any ring, okay, and then you take a left or free module, then you may have this situation that M is different from N and still they're isomorphic, right? So this is what we call the non-invariant basis number property. And in early 50s, Bill Leavitt gave a precise construction for rings which will defy invariant basis number property. So they will have this situation that you will have M different from N and still this free module will be isomorphic to this one. If you're interested, you can look for a paper of Bill Leavitt. It's from Transactions of MS sometime in 53 or 52. I guess the title is something like module type of a ring. But here is a small exercise for any motivated young researcher. At least this much you can try to prove. If R is a ring with generators x1 through xn, y1 through yn, such that yi xj is delta ij, and summation over I from 1 to n, xi yi equals 1, then in that case, this free R module would be isomorphic to this one, right? So you should try to, so this is an exercise for you, try to prove this. So that's one motivation. We'll see a construction of a path algebra where you can readily construct examples of rings defying invariant basis number property. And the second motivation comes from graph C-star algebras. So let me quickly tell you what graph C-star algebras are. So take a quiver, a directed graph, okay. So vertices, so I'm denoting by E naught, the set of vertices, by E1, the set of edges, and two functions, let's say S and R. So what are these functions? So S and R, these are functions from E1, the set of edges, to set of vertices. So if you have an edge, okay, an arrow from A to B, call this edge or arrow E, then source of, so S is source, okay, so S of E is A and R of E is B, right? So this is source and this is range. So a quiver or a directed graph, it has essentially these data points. So you have vertices, you have edges, and you have a source function, and you have a range function, right? And so the graph C-star algebra, which was studied by people working in operator theory, they defined this as a universal C-star algebra generated by orthogonal projections and partial isometries satisfying the two conditions that if V is a regular vertex in the sense that it is not a sink. Sink means what? Just the word, the choice of the word tells you. Sink means a vertex where everything reaches here, the arrows, but it doesn't emit any arrow, right? So that's a sink. And if it is not an infinite emitter, so it doesn't emit infinitely many edges, then you have this, and the other condition is you have maybe this, then right. So partial isometry means you know, if you have an operator x star x is a self-adjoint operator, right? So now, motivated by this, we define Leavitt path algebra over this quiver in the following way. So Leavitt path algebra is a K algebra generated by these vertices, edges, and ghost edges. So I'll explain what we mean by ghost edge. So ghost edge means every time you have an arrow from say A to B, then we assume an arrow going back. Okay, so this is just in our head. This is not given in the quiver. We always to every arrow E we associate an arrow going backward. Since it is not there and we are imagining it, we call it ghost arrow, right? So it is a K algebra generated by vertices, edges, and ghost edges, subject to the following conditions. The conditions are that these vertices are orthogonal idempotents, in the sense that if you take Vi square, that is Vi, and if you take Vi Vj, I different from j, then this is 0, right? So vertices form an orthogonal family of idempotents. If you take an edge, you multiply with the source, you get E back, you multiply with the range. So this is essentially telling you the compatibility in a concatenation of paths, right? So same thing for ghost arrow. So not too difficult to see that source of E star would be same as range of E, right? Because E star is backward. So so everyone with me so far? Right. So these conditions, and then the two conditions borrowed from the theory of graph C star algebra. So we call them CK1, so Kunj-Krieger 1 condition, which is if you have E star E, that is range of E, and if you have E star F, then that is 0. And Kunz-Krieger 2 condition, that if V is not an infinite emitter, and not a sink, then V is sum of E star for all the edges E in E1 with source of E equals V, right? Does that make sense? So this is what Leavitt path algebra mean. It's a K algebra, and it is universal with this property, in the sense that if you take any other K algebra with generators satisfying this kind of relation, then there is a homomorphism between the two algebras. So this is a universal K algebra with this kind of relation, right? To see some quick examples, if you have not seen it before, maybe this will make your life easier. Let's take a very simple case. Suppose I take two vertices, V1 and V2, and I take just this edge E. Okay, then it's not too difficult to see that this Leavitt path algebra is just the 2 by 2 matrix ring over K. Under the very quick identification, you can associate V1 with 1 0 0 0, V2 with 0 1 0 0, E with 0 1 0 0, and E star with 0 0 1 0. You can check that all the conditions that I mentioned here, they will be satisfied, right? And so, well, the story goes on, and if we have the same kind of situation, so if you have this Dinkin diagram of type AN, so this n vertices, right? Then here the Leavitt path algebra would be the n by n matrix ring over K. If you just take a vertex and a loop on that, you can check. Again, this is not too difficult to see. This one will be isomorphic to this Laurent polynomial algebra. Okay. All right. So this is what Leavitt path algebra is. How much time do I have now?
10 minutes.
10 minutes. Okay. All right. Okay. So I hope I'm able to convince you that it's a nice class of algebra. And as you have seen, just if you look at the way we are multiplying things, you can see it's highly non-commutative, right? Because the order here really matters. But one thing quite surprising here is the ideal theory. The ideals have property more like commutative rings, which is kind of very surprising. So, well, one thing you can again notice is that this is a Z-graded algebra, right? So Leavitt path algebra is a Z-graded algebra in a very natural way. You can give the grading of vertices. You can give 0. You can give edges degree 1, and the ghost edges can degree negative 1, right? And so it's not too difficult to see that this. So suppose I denote this as L. L is direct sum of Ln, where you can write. So actually, any monomial is going to look like a alpha beta star, where this is a path and this is a ghost path, right? And so you really want length of alpha, length of beta to be n. More than that, you can actually see this is a differentially graded algebra, but I'll not get into that. Those who are interested, you can actually think a little bit, and you can actually see this is a DG graded algebra. So, so what happens is that if you take two ideals, when one of them is graded, so if A is graded and B is any other, and when I say ideal, that means two-sided ideal, right? Then something very interesting happens. AB equals BA, right? That's very surprising. My one PhD student proved a very nice result. So, you know, from, again, in your early undergraduate courses, you must have proved that if you take two integers, say m and n, then least common multiple of m and n, and you take the greatest common divisor, you multiply them, that is same as m times n, right? Using fundamental theorem of arithmetic, you can quickly see this. So she proved an analog of this for ideals in Leavitt path algebra. She proved that if A and B are two ideals, two-sided ideals in a Leavitt path algebra, then A intersection B multiplied to A plus B equals AB, which is just the ideal theoretic analog of this beautiful property of integers, right? And my current PhD student who is going to defend very soon, actually I'm now going to wrap up with her results. So she has studied some nice properties which I really wanted to advertise. So things which are like classic things in commutative ring theory. You have notion of prime ideals, right? So you have prime ideals in commutative rings. So when you go to non-commutative rings, you just, instead of elements, you define in terms of ideals. So you say an ideal P will be prime if anytime AB is contained in P, that implies A is contained in P, or B is contained in P, right? So that's something you learn in your graduate algebra class. Another notion related to that is the notion of irreducible ideal. So irreducible ideal means if you have any two ideals A and B, and A intersection B equals I, that implies A equals I or B equals I, right? So just the ideal theoretic analog of what you call irreducible elements. And then there is a stronger version of this. So strongly irreducible ideal is A intersection B contained in I implies A is contained in I or B is contained in I, right? It's not too difficult to see that every prime ideal is strongly irreducible, and every strongly irreducible is irreducible in any ring, right? However, in an arbitrary ring, you can quickly find example where this doesn't go back, because, and just take the ideal 8z, for example, right? In ring of integers, that is strongly irreducible. This is an exercise for you. You can check that 8z is an irreducible, strongly irreducible ideal in ring of integers, but it is not prime because it is not a prime. To see irreducible which is not strongly irreducible, again, small exercise for you. Take the polynomial ring in two variables, x and y, over Q, and you can check that ideal generated by x and y square, for example, this is irreducible, but it is not strongly irreducible. But then my student in her dissertation has proved something very interesting, that for Leavitt path algebra, the three notions are equivalent. So the following are equivalent for L equals LKE. I is strongly irreducible. I is irreducible, and this is equivalent to saying I equals P to the n for some prime ideal. And I'll just quickly finish in 2 minutes. So as I said, there is a beautiful analog of all the factorization theory of ideals, what we know classically from the case of commutative rings, going back here. So there is an old question of William Heinzer where he asked under what conditions every ideal in a commutative ring is an irredundant intersection of irreducible ideals. And again, my student in her dissertation has given a complete answer for this thing in case of Leavitt path algebra. So I'll just quickly mention her result. I think that's a beautiful result. Um, so for L equals LKE, the following are equivalent. A, that every ideal of L is an redundant intersection of finitely many irreducible ideals. In fact, this is equivalent to saying same thing with instead irredundant intersection. You can replace that by product of irreducible ideals. And the characterization here is that every non-zero homomorphic image of L is either a prime ring or it contains finitely many minimal prime ideals. And this is equivalent to saying for every, and this is very technical, so I'm not going to define it, but this is more combinatorial. For every admissible pair HS, the vertices in the quotient graph is a finite union of maximal tails. So maximal tail, maybe just one more minute. Maximal tail means, so if you have a subset of vertices, we say it is a maximal tail. Actually, you can actually quickly visualize. The first thing is that it is downward directed, in the sense that if you take any U and V in M, then there is a W in M, such that there is a path from U to W and there is a path from V to W. And second thing is that anytime if U is in M and V is any other vertex with a path from V to U, then V is in M. And the third property we want is that if U is in M, then there is at least one edge with source of E equals U and range of E being in M. All right, I'll stop here. Thank you.
Thank you, sir. If anyone in the audience has any question, please unmute yourself and ask your question.
कोई कुछ नहीं पूछेगा प्रतिभा वो कहीं चली गई क्या आप अनम्यूट हो आप नहीं आप अनम्यूट हो आपकी आवाज आ रही
Good morning, sir. Sir,
Do you have a question?
Hello, can you hear me?
yes
Yeah.
Okay, good morning, sir. My question is this. Actually, I was doing my research in the graded algebra. Somewhere you have connected to Leavitt path algebra. Then later you explain about the graded. A is a graded and B is any other ideal. Then the properties you have explained, AB is equals to BA, where A and B both are the ideals. Further, you have talked about the LCM and GCD. Then the one property you have taken, A intersection B into A plus B is equals to AB. So Can I get by any example to elaborate this to get to know?
Yeah, you can check in. I mean, um, that's true for any two-sided ideals. So if you want to see an illustration, you can actually go to papers
Okay. And sir,
of my students.
okay. One more thing.
You know, constructing. So maybe one quick thing I can tell you is that, so if you're wondering how do I construct ideal,
Yes, sir.
graded ideal,
Yes.
right? So graded ideal, construction of graded ideal is very easy, because there is a very beautiful result due to Mark Tomford, which says that every graded ideal of Leavitt path algebra looks like this, where this is an admissible pair. What do I mean by that? So H is a hereditary set. Hereditary, the name tells you what hereditary should mean. So hereditary means that anytime if U is in H and there is a path from U to any vertex V, then V is in H, right? So hereditary. If something is there, then every vertex that comes along the path of that vertex is also in H. And saturated means, so if range of S inverse V is contained in H, then that forces V to be in H. Okay. So now if you have a hereditary saturated subset H, okay, then there is a notion of what we call breaking vertex. So breaking vertex is an infinite emitter. W is an infinite emitter in E0 without H, with the property, and this is a bit technical. And then we denote the set of all breaking vertices by, say, B sub H. So you take any subset S of this breaking vertices, then this pair is called an admissible pair. Okay. And so you take any vertex generated by H, and again, a lot of symbols. So V sub superscript H means I'm writing V minus E star. Okay. So the ideal generated by this is what I denote as IHS. And this is precisely any graded ideal of Leavitt path algebra, right? So all you do is you take any quiver, you take any directed graph, find a hereditary set, find a hereditary saturated set, and find breaking vertices, take a subset of the breaking vertices, and you generate any ideal with this as generator. That will be your graded ideal.
Okay, thank you very much, sir. It means we can generate the graded ideal by using the Leavitt path algebra. Okay, thanks a lot, sir, and it is very useful words which you have shared and knowledge. Thanks a lot.
Thank you for asking. Yeah.
Thank you, sir. We are very grateful to you that apart from having a busy schedule,